Hello folks, today we're going to be working on the 40s, which is a topic that has a name called stoichiometry. It might seem new, but it's actually stuff that we've already kind of encountered already. Today we're going to be really going between these two islands right here, and we're going to be using coefficients to solve a lot of our problems. So stoichiometry notes, here we go. Stoichiometry is equal to the quantitative or the number of mole relationship between reactants and products using coefficients and sometimes subscripts. Subscripts can be used as mole ratios, such as this 2 in H2O. So there's 2 hydrogens in every water molecule. Coefficients can also be used, these are the numbers out in front, such as there's 4 moles of potassium nitrate. Both have infinite sig figs. And again, we're going to be concentrating on this bridge right here for most of our problems today. If you need to determine how many atoms there are in a molecule, you would use subscripts. If you need to convert the quantity of one chemical compound into the quantity of another chemical compound, you would use coefficients. Again, this is where we're going to play today. And we're going to use coefficients and subscripts, both with infinite sig figs. In 1 mole of water, there are blank mole of hydrogen and blank mole of H2O. So, in 1 mole of H2O, there are 2 moles of hydrogen and 1 mole of oxygen. See if you can do this one before I fill in the blanks. So pause and see if you can do this one on your own. In 1 mole of CO2, there's 1 mole of carbon and 2 moles of oxygen. Again, pause it before you do the next problem. See if you can do the next problem on your own. In 1 mole of zinc acetate, which is C2H3O2, and then you need 2 of those to balance out the zinc, there are 6 moles of hydrogen. So there's 3 there, and there's 2 of these acetate molecules, so that's 6 moles of hydrogen and 4 moles of oxygen. Again, try this problem on your own before you progress it any further. Ag2SO4 to balance the charge. In 1 mole of silver sulfate, there'd be 2 moles of silver and 4 moles of oxygen. All right, we're on the back side at this point in time. We're going to use this balance equation that's there for us. When there are 2 moles of H2, and you burn, and you have 1 mole of oxygen are used, and 2 moles of H2O are produced. So that's using stoichiometry in its very basic format. Try the next problem on your own before you watch me solve the problem. When there are 2 moles of Fe, that's iron, when those burn, you'll need 3 moles of O2 are used, and there you end up producing 2 moles of iron oxide, Fe2O3. Try number 7 on your own before you watch me do it. So we have 3 moles of hydrogen gas. Now remember, hydrogen's diatomic, so if you're going to have pure hydrogen gas, it's going to be H2. Plus 1 mole of N. But nitrogen is also diatomic, so that's got to be N2. And that's going to form 2 moles of ammonia, which you're probably unfamiliar with. Now, when I really write the balanced equation, I'm going to go 3H2 plus 1N2, and the 1 is optional there. It's going to make 2NH3. That's how I would really write that particular balanced equation. Number 8, the formula looks a little bit longer, so it might look a little bit more confusing, but I think you'll be able to handle it just fine. So it says in a reaction, gases are represented by G, L is for liquids, S for solids. So you're going to see those starting to pop up in some of our balanced equations every once in a while. Sometimes they're important, sometimes they're not really giving us much information. Including the phase is sometimes important, it says. In a combustion reaction, energy is released, ensures that water produced is in the gas phase. It says for A, how many moles of gas are produced when 2 moles of butane are burned? Well, this is butane right here, and it wants to know how many moles of gas are produced. Well, here we have 8 moles of gas. And here we have 10 moles of gas, so we get 18 moles of gas are produced. So the next question asks, how many moles of gas are burned when there's 4 moles of butane that are burned? Well, if 2 moles gave us 18 moles of gas, if now I have 4 moles of butane, I have double the amount of butane, I should double the amount of gas. So 18 plus 18 equals 36 moles of gas. So that problem seemed a little bit more difficult than it actually was, but that's the way it goes sometimes. Number 9. It says use a mole-to-mole conversion factor and the reaction below to calculate how many moles of oxygen are made when 3.55 moles of potassium nitrate decomposes. Again, subscripts and coefficients have infinite number of sig figs. So looking at the mole map, I am starting here with KNO3, and I am going to moles of oxygen. So this is actually a fairly simple problem. I start with what they give us, 3.55, and potassium nitrate is KNO3. Multiplication sign, division bar. Whatever this label is here, it goes right down here. So KNO3, and this would be moles. And we can go from moles of KNO3 right to moles of oxygen. So moles of O2. To go across from mole island to mole island, we have to go across that bridge, and that's called coefficient or subscript bridge. So in this problem, we have 4 for the KNO3, and the oxygen we have a 5. Remember, both of these are infinite sig figs. So we should have a 3 sig fig answer when it all comes to the end. So when we solve this on a calculator, we get 4.4375. We can only have 3 sig figs in our answer, so our answer would end up being 4.44, and that would be moles of oxygen. Because moles of potassium nitrate cancel out with moles of potassium nitrate. And my mistake, I forgot to write moles there to begin with. Naughty me. We're actually going to go to the next handout then, which would be the 45s, and we're going to do the first 2 problems on the 45s. So we're going to go to the 45s, we're going to use that same mole map, and we are going to solve this problem. So in this particular problem on the 45s, it says there's 2.444 times 10 to the 24th molecules of hydrogen, and how many moles of ammonia could you make from that? That's assuming that you have enough nitrogen, and there's plenty of nitrogen in our air. So you're going to start off with what they give us, the 2.444 times 10 to the 24th molecules of hydrogen. Now we probably should look and see where we're going on our mole map. We're starting over here with molecules of hydrogen, and it wants to know how many moles of ammonia. So we're going to go over here, and then we're going to have to go down and end up over here. So we should have two multiplication signs in this problem. So we put a multiplication sign in a division bar. Remember, whatever label is right there goes right there. So this is going to be molecules of H2. So we're right here, and we have to go right here. So to go from molecule island over to mole island, we can do that. We have to write mole and H2. Now I'm going to have to shoot this over here so I have a little bit more room to work. So what was on top goes on the bottom. So moles of H2 go on the bottom. So that means we're right. I'm going to clear off my map right now. Right now we are here at moles of H2, and we're going to go to moles of ammonia. So we can do that. Moles of NH3. Now we pop in some numbers. So the bridge right here is 6.02 times 10 to the 23rd bridge. So that's 6.02 times 10 to the 23rd molecules are in 1 mole of hydrogen gas. When we go between mole and mole, we use coefficients from the equation. So here's a 3 and here's a 2. So the 3 goes with the hydrogen and a 2 goes with the ammonia. I get my answer for this problem, and it's 2.70653 moles of ammonia. But now we got to go back and look at sig figs. Here I have 4 sig figs. Here I have infinite. Here I have 3. Here I have infinite. Here I have infinite. So if I look at all that, my smallest number of significant digits is 3. So this would be 2.71 moles of NH3. If you want to look at a prettier version of that, right there you go. Try to do the next problem all on your own before I do it for you. All right, in this problem, let's look at the mole map and see where we're starting off and where we are going. So it looks like we're starting off on Graham Island for iron oxide, and we want to go to moles of iron, so we have to get down here. So our map is to go from Graham Island over to mole island down to mole island. So very similar to the last problem, except we're starting with grams. So we start with 7.777. Oh, let's start all over again because I put the decimal spot in the wrong place. So 777.77 grams of iron 3 oxide, Fe2O3. Whatever that label is goes down here. Grams of Fe2O3. If we're on Graham Island, the only place we can go is to mole island. So this would be moles of Fe2O3. Once we're over here on mole island, so this would be moles of Fe2O3. I gotta put an E in there. We're right here. We're going to go down to mole island of iron. So it's going to be moles of Fe. Now we'll go ahead and we'll put in some numbers. So right here, this bridge is molar mass bridge. So that means we got to go get a number off the periodic table. So this would be 159.70 is 1 mole. Right here is coefficient bridge. So there is a 2 in front of the iron 3 oxide. and there's a 4 in front of the iron, so I put a 4 and I put a 2. I go ahead